Hello, everyone. So, as promised, this is going to be an introductory video to the WEAR project. WEAR stands for Wearable Electromyography Analysis for Rehabilitation, or Wearable EMG Analysis for Rehabilitation. This is a project that was initially done by 2012 by a master's student at Carleton University, and later on it continued to make it a real world project or get a real world product going. Uh, it was continued at Algonquin College by multiple teams. Bear with me, I'm more of an electronics and electrical engineering person, not a biology person, so I'll try and explain everything from the beginning. So, the current phase three, we are the third team to attempt this project, and I have two other students with me. One is a mechanical engineer, and the other is from an electrical engineering team. Our clients are Dr. Chan, Adrian Chan. He's from the Department of Systems and Computer Engineering, Carleton University, and Dr. Edward Lamar, uh, University of Ottawa and Ottawa Research Rehabilitation Engineering Center. So today I'll just give you a brief overview of EMG, electromyography, a brief background of the WEAR system and its history, how it came to be, and the scope of the project, or what WEAR stands for, or like what is it trying to achieve in the end. This is just going to be an introductory video, so I'll try and keep it as brief as possible. So EMG stands for electromyography. It is just a technique that records electrical activity of muscles and muscle tissue. It takes that data, it represents it as a visual display or an audible signal, and it uses electrodes that are attached to the skin or inserted into the muscle. Now, our project is mostly focused on surface electromyography, which is a non-invasive technique, uh, which means that we don't actually inject the electrodes into a human subject. It's surface on the skin. Now, EMG allows doctors to measure a patient's muscle function during motion and things like strength and timing of muscle contractions. It's a very useful tool because it is used to identify lots of neuromuscular diseases, or sometimes as a research tool for studying kinesiology, and also other disorders of motor control to diagnose them. Sometimes it's also used to guide specific injections into muscles. Lately, it's also there's a rise in using EMG signals as a control signal for prosthetic devices such as arms, legs, lower limbs, things like that. Now, generally speaking, EMG signals they range from below 50 microvolts uh, up to 20 to 30 millivolts, depending on the contraction, muscle size, things like that. And in terms of frequency, they have a range from between 30 to 300 hertz. As you can see, 50 microvolts is actually quite low. That's a very, very small signal, and because of this, it makes the whole data acquisition process very susceptible to external noise. Things like motion, drift motion, interference from power lines, or any other electromagnetic noise caused by RF or any nearby equipment. As you can see here, this is like a typical EMG signal or something that it would be measured on a screen, but it looks like noise. There's no way of telling whether this is a real signal or not. So there's been a lot of filtration techniques that have been developed specifically for this. And when you clean up the signal, it looks something like this. So every time you see a bunch of signals bunched around like this, that's a spike. So that means the muscle is moving. And this is a baseline. That's when there's no activity. Now, usually, it differs from ECG in a very significant way. ECG is electrocardiography, where you're measuring the signal from the heart. You see clean spikes when the heart beats. There's a reason. The heart is, after all, a muscle, but it fires in synchronity, which means like all the muscles of the heart they fire together, which is why we get a nice clean signal, clean spike. In terms of EMG, on the other hand, your muscles do not fire in synchronity; they fire asynchronously, which is why we don't get weird jutting motion. We get fluid motion that looks organic. Now, traditional EMG system that's used, it requires a trained individual to operate it. That there are sessions involved. It takes several hours. You have to install electrodes, book appointments, and the operating and purchasing costs of equipment like this are very prohibitive. Uh, this process, like, it alienates small private physiotherapy clinics from becoming end users. So only big hospitals or research centers can use something like this. Uh, so this is a brief history. This is what electromyography is. So one of the student, the initial master student who came up with this thesis, he found that there was an actual need for a surface electromyography system that is that was clinically feasible, which meant it can be used in clinics, as well as a end user could buy this thing off the shelf. It would be cheap enough or inexpensive enough that somebody could just buy it off the shelf and install it themselves, use it at home, record the data, and maybe send it off on the cloud or like online to a doctor for post analysis. Now I'll give you a brief history of the WARE project itself. Brief background, actually. So in 2012, there was a student, his name was Adam Freed at Carleton. He was a master's student. For his final thesis, he came up with, he envisioned this system that would be very, very small, modular, could be easily obtained by an end user. He did his thesis under Dr. Adrian Chan and Dr. Lamar, and I'll be posting links in the description to his work and his work on his research on gait analysis, as well as all the data he collected over that period of time. After he graduated and moved on, I guess the project was brought to Algonquin College in 2017 and 18. And the first phase of electrical engineering technology students attempted to make this project a reality. They ended up changing much of the original electronic components that we use, just because technology had evolved quite a bit, and they added things like Bluetooth and a micro SDXC card for data storage. The original prototype uses an electrode sleeve array. So instead of having a lot of electrodes just coming and being installed individually, there's a sleeve built which has about 8 electrodes that can easily just be slipped on by a user. This sleeve would tie to a bioamplifier, which the chip he used was ADS1298. It's a chip made by Texas Instruments. It's an 8-channel, 24-bit analog front end. It's designed specifically for biopotential measurements. It's also very, very, very energy efficient. And he used a 16-bit flash microcontroller, general purpose PIC, also an SD flash memory card from Microchip, and a Bluetooth transceiver. So at the time, we have access to these components, obviously, but they were pretty huge, and it was quite hard to create something small and something wearable. And all in all, so the ADS chip itself, it has 8 integrated programmable game amplifiers. Can be programmed. The PGA can be programmed from 1 to 12. They're high resolution A to D converters and has a very, very small packet size, 8 millimeters by 8 millimeters. It's also fairly inexpensive, about $50 just for the IC itself. In terms of bandwidth, 500 hertz is often used for sEMG applications, which means 500 kilosamples per second. But this usually our system right now, it's functional at 1,000 samples per second, which is more than enough. And this ADS1298 chip that we're using, it gives us up to 32 kilosamples per second, so it's more than enough for what we need. So the architecture is simple. This electrode sleeve will tie on to the bioamplifier, which will in turn tie on to a microprocessor that's used. There'll be an SD card involved, as well as a Bluetooth section where the data will be sent across Bluetooth to an app or a PC, so a user can actually visualize and see, make sure it's working, make sure everything's in order before pressing record on the on the peripheral itself, and then the controller will record all 8 channels straight to the SD card, after which the SD can be easily recovered for post-processing. Now I'll break down the actual scope of the project of the Wear system. Obviously it needs to be a user-friendly device, something very interactive, nothing complicated. It needs to have very short procedure times, easy to set up. It needs to acquire data from all 8 channels of the amplifier, 2 channels of data visualization. So we need to have at least 2 channels graphed so the user can actually see it's working across Bluetooth. It has to have 2 to 8, or ideally all 8 channels data logging on the SD card. It needs to have automatic signal detection, live updates, obviously a removable data storage for post analysis, and the key here to make it portable is needs to have a battery, a rechargeable battery. Now I'll break down the sequence of events that needs to happen. So there's a electrode sleeve that I talked about a bit about earlier. It contains a bipolar array of electrodes, silver. They're made from silver due to conductivity purposes. So initially, a user should ideally install the sleeve on his arm or leg. The signal that's picked up from the electrodes will be transmitted to the analog front end, which in this case is the ADS1298. It will connect the data. It's a high 24-bit high precision converter. It will pack that data nicely, uh, and it will transmit that data to our microcontroller over SPI. SPI is Serial Peripheral Interface. It's a high-speed communications protocol, and the microcontroller will apply a software filter, which is originally built in MATLAB, in order to get data off and translate it from bits to its actual raw voltage values that it's seeing. So the reason it does that is because it sends that data, the raw voltage values, to across Bluetooth to an Android app. So a user can actually see two channels being plotted and active at a time. And the user can actually cycle through two channels at a time to see that all 8 channels are working before pressing record. After pressing record, the microcontroller should log all 8 channels, or it logs all 8 channels of data at 1,000 samples a second minimum to the onboard micro SD card, which can be later recovered for future analysis. So this is a brief overview of the Wear system or how it should function. That's it for this video. Please subscribe to our channel if you like this video or you like the idea of this project. Don't forget to add comments for anything that you thought or you think